Welcome to YouTube channel. Myself, Dr. E. Kumraya, Assistant Professor of Mathematics, Sri Rajarajeshwara Gout Arts and Science College, Karimnagar, Telangana, India. Today I am going to discuss about solution to linear system of equations by using rank method. That means the system of equations can be put in the form of ax is equals to b, then solve the system by using the rank method. Now let us consider the linear system which consists m equations and n unknowns. The equations are m, the number of unknowns are n. Let us suppose we consider the system with 3 equations and 4 unknowns, that is a11x, a12y, a13z, a14w equals to b1, a21x, a22y, a23z, a24w equals to b2, a31x, a32y, a33z, a34w equals to b3. Here all a11's, ai's and bi's are constants. X, y, z, w are the parameter variables. We have to find x, y, z, w which satisfies all these simultaneous equations. That is our problem. To solve this system, we consider the system can be put in the form of ax equals to b, where a is the m by n matrix and x is the column vector in Rn and b is the column vector in Rm, and this can be put in the form of ax equals to b. After this, we consider the augmented matrix AB. A and side by side matrix B, column matrix can be put. That's why after considering the augmented matrix, find the rank of AB. Now, the popular condition is the system is consistent if rank of A is equals to rank of AB. If rank of A and rank of AB is same, then only the system is consistent. Otherwise, that means rank of A not is equals to rank of AB, then the solution is inconsistent. The solution may not possess the system does not possess the solution. In the case of rank of A not is equals to rank of AB, if suppose the system is consistent, that is rank of A equals to rank of AB equals to some number R, both are equal to some R. Now if R is equals to number of unknowns, unknowns means number of columns, if the rank is equals to number of columns, the system has only one non-zero solution, unique solution. If otherwise, if R is less than number of unknowns, R is less than number of columns, then the system possesses infinite number of solutions. Depending on these conditions, we can decide how many solutions the system may possess, either unique or infinite number of solutions. Now let us consider the system. One simple example: x plus y is equals to 1 and x plus y is equals to minus 1. That is, this can be put in the form of the matrix 1 1 1 1 xy equals to 1 comma minus 1. Now consider the augmented matrix AB is equals to 1 1 1 1. This is A and B is 1 minus 1 column wise. That is, this part is A and this part is B, A, B. And by applying the elementary row operations, we reduce this into row echelon form. For that, we apply the row operation R2 implies R2 minus R1. By taking R2 minus R1, 1 minus 1 0, 1 minus 1 0, minus 1 minus 1 minus 2. Now here, now decide the rank of A and rank of AB. This is the matrix A. For this matrix A, rank of A is 1. The number of non-zero rows are only 1. That's why rank of A is 1. And consider AB. This is matrix AB. Rank of AB. In the matrix AB, number of non-zero rows are 2. That's why rank of AB is 2. Therefore, rank of A equals to 1, which is not equals to rank of AB. That's why the system may not possess the solution. Or we can directly understand that x plus y is equals to 1 and x plus y equals to minus 1. It is impossible. For same values of x and y, x plus y will become 1 and x plus y will become minus 1. It is impossible. That's why the system cannot possess the solution. It satisfies the simultaneous equations. Or we can we can go for another example. Consider the one more example. X plus 2y plus 2z equals to 1, 2x plus y plus 2z equals to 1, 2x plus 2y plus z is equals to 1. This is another system. This is 3 equations and 3 unknowns involves, that can be put in the form of ax is equals to b 1 2 2 2 1 2 2 2 1 x y z 1 1 1. This is the ax equals to b. First we consider the augmented matrix. Any system is given to you, first thing is we have to consider the augmented matrix AB, that is A and B. Matrix is combined with A and B, that is 1 2 2 2 1 2 2 2 1 and B is 1 1 1 1. This is AB, and reduce it to row echelon form by using the elementary row operations. That is R2 implies R2 minus 2R1. Similarly R3 implies R3 minus 2R1. Multiply R1 minus 2 and subtract from R2 and subtract from R3. The resultant matrix is 1 2 2 1 0 minus 3 minus 2 minus 1 0 minus 2 minus 3 minus 1. Now still it is not in the row echelon form. That's why we can apply the again one more row operation by using this element. Earlier case using this element. This is multiplied by minus 2, add to R2 and R3, and now we use this. In the second step we apply the elementary row operations by using second row, that is by using minus 3 we make minus 2, this place of this element should be 0. For that we multiply this by multiply R3 by 3 and R2 by minus 2. Then the resultant matrix will be 1 2 2 1 0 minus 3 minus 2 minus 1. The two rows cannot change, and last row will be changed by applying the elementary row operation using R2 to 0 0 5 1. Now it is in the row echelon form. Then what is the rank? Decide the rank of the matrices. What is the rank of A? This is matrix A. In this matrix A, the number of non-zero rows are 3. That's why rank of A is equals to 3. And the rank of AB, entire matrix, number of non-zero rows also 2, 3. That's why rank of AB is also equal to 3. Therefore, rank of A equals to rank of AB equals to 3 equal to number of unknowns. Unknowns also equals to 3. That's why the system passes only one solution, that is the reduced equations. The reduced equations are by backward substitution. You come from the bottom, that 5z equals to 1. This is 5z equals to 1. 5z equals to 1. Z is equals to 1 by 5. Now second equation, we consider the second row. Minus 3y minus 2z equal to minus 1. Minus minus will be cancelled on both sides. That is 3y plus 2z plus 1. Then solving for y is equals to 1 by 3, 1 minus 2z. Already z is equals to 1 by 5, substitute here. Then we get y is equals to 1 by 5. Similarly, consider the last equation, that is top of the matrices, first row, that is x plus 2y plus 2z equals to 1. This is x plus 2y plus 2z equals to 1. By substituting y is 1 by 5, z is 1 by 5, we get x is 1 by 5. Therefore, the system has unique solution, that is x equals to y is equals to z is equals to 1 by 5 unique solution, because rank of A, rank of AB equals to number of unknowns. Now consider the one more example, x minus y plus z equals to 2, 2x plus 2y minus z equals to 3, 3x plus y is equals to 5. This is also a system with 3 equations and 3 unknowns. This can be put in the form of 1 minus 1, 1, 2, 1, 2, 2 minus 1, 3, 1, 0, x, y, z, 2, 3, 5. Now let us consider, first we consider our goal is first consider the augmented matrix to solve the system. Whichever it is, How many variables are involved, that is not matter. Just we consider the augmented matrix AB. This is the matrix AB and reduce it into row echelon form by using suitable row operations, that is R2 implies minus 2 into R1, R3 implies minus 3 into R1, R3 minus 3 into R1. Then the reduced matrix, the transformed matrix is 1 minus 1 1. The first row cannot be changed. Next two rows will be changed. 0 4 minus 3 minus 1, 0 4 minus 3 minus 1. And again, now here we can observe that the two rows are identical here. This one, this row and this row, two are identical. 4 4 minus 3 minus 3 minus 1 minus 1. These are identical. Now by applying again row operation, R3 implies R3 minus R2. Then the resultant matrix will be, that last row will become 0 0 0 0. Now decide the rank of A. Rank of A is, this is A. In this A, number of non-zero rows are 2, and entire B also number of non-zero rows are 2. That's why rank of A equals to rank of AB equals to 2, which is equals to number of unknowns. That's why the system has infinite number of solutions. So many solutions it has. Now the reduced equations are, only there are two original equations. That is, first one is 4y minus 3z minus 1 equal to minus 1. We solve this for z. Z is equals to, in terms of y, 1 by 3 plus 4y by 3. This is the z value. Again we consider another equation, that first row, using first row, x minus y plus z is equals to 2. By substituting z is equals to 1 by 3 plus 4y by 3, we get x is equals to 5 by 3 minus y by 3. Then the solution is, x is equals to, capital X is the solution vector. So solution vector is equals to, small x is 5 minus y by 3, and y is the independent variable parameter, that is y, and z is 1 plus 4y by 3. Here we split this solution vector into two vectors. One is independent of y vector, that is 5 by 3 0 1 by 3, and another one is minus 1 3 4 into t. T is the parameter, that is y is equals to, when y equals to 3t is the parameter. Now here there are two solutions. 5 by 3 0 1 by 3 is always a solution, which is called particular solution, and minus 1 3 into 3 4 into t is a complementary solution. For this solution, ax equals to, ax will become 0. For this particular solution, 5 by 3, this is the particular solution, 5 by 3 0 1 by 3, it does not involve any parameter. This is the complementary solution, which involves parameter t. For any value of t, it is a solution. For any value of t, ax will become 0. But for particular solution, ax will become b. Ax will become b. That's why this is called particular solution. This is called complementary solution. For any value of t, this is complementary. Ax will become 0. Okay. Now we can consider another particular case, that is homogeneous system. Let us consider the linear system with m equations and n unknowns. The right hand side will be 0. This is the system ax equals to 0. This is called homogeneous system. Previous one is called non-homogeneous system. B naught is equals to 0. That is non-homogeneous system. B is equals to 0. Homogeneous system. This can be put in the form of ax equals to 0. X is in Rn. 0 is in Rm. That is put in the matrix form like this. Now we decide the consistency of this system. In the earlier case, the condition for the consistency of the system is rank of A is equals to rank of AB. But here B is 0. That's why rank of A equals to rank of A, B 0, it is equals to rank of A. That's why this homogeneous system is always consistent. Or because for homogeneous system, Ax equals to 0, 0, 0, 0, 0, 0 is the always solution for this system. That's why this is always consistent. In the earlier case, B not 0, then 0, 0, 0 is cannot be solution. That's why it may not consistent or consistent. But here, in the case of homogeneous system, it is always consistent, always 0, 0, 0. 0 is a solution for the Ax equal to 0. This is always consistent. Now, if it is consistent, how many solutions it consists? Or when the system Ax equals 0 consists a non-zero solution. Zero solution is always solution. That is okay, fine. But when it consists a non-zero solution, for that, if rank of A equals to R, if R equals to number of columns, number of unknowns, the system has only one solution, that is zero solution. That is earlier already we discussed that equals number of unknowns. It has only unique non-zero solution in the earlier case, but here unique zero solution. If rank of A is number of unknowns, system has only one solution, that is zero solution. If the rank is less than columns, number of unknowns, then the system possesses non-zero solutions. This is the popular condition. If R is less than number of unknowns, system possesses non-zero solution. How many non-zero solutions? It is not unique, infinite number of non-zero solutions. This you should remember. Now, from this we can conclude that if suppose a system is given to you, in that system the equations are less than unknowns, we can directly say that the system possesses a non-zero solution. Equations are less than unknowns. Suppose 2 equations is there, 5 unknowns is there. We can directly say that the system possesses non-zero solution. Zero solution also, it has zero solution also. Zero solution is always a solution, that is no matter. But it is also possesses non-zero solution. If number of unknowns equals to number of equations, that means matrix is square matrix, coefficient matrix A is square matrix. In this case, if rank of A is less than unknowns means det A is 0. If det A is 0, it possesses non-zero solutions. Det A is non-zero means rank of A is n equals to number of unknowns. That's why it possesses zero solution only. That means we conclude that if for Ax equals to 0, A is a square matrix, then if det A equal to 0, the system possesses a non-zero solution. If det A not 0, the system possesses only one trivial solution, that is zero solution. These conclusions you keep in your mind always. Det A 0, non-zero solution. Det A not 0, only zero solution in the case of A is square matrix. Now, we can consider some examples. This is x plus 2y plus 2z equals 0, 2x plus y plus 2z equals 0, 2x plus 2y plus z is equals to 0, that is put in Ax equals to 0. Whenever system is homogeneous, simply we consider matrix A only. It is not necessary to take AB. It is only take A and reduce A into its row echelon form and decide the rank of A. Now here, this is already done in the earlier case for Ax equals to B, B not 0, but here B is equals to 0. By reducing it into row echelon form, we get 1, 2, 2, 0, minus 3, minus 2, 0, 0, 5. Rank of A is equals to 3. That's why solution is unique zero solution. That is given by 5z from backward substitution. This is 5z equals to 0. Right hand side is 0. 5z equals to 0. That's why z is equals to 0. Then y equals to 0. Then x is equals to 0. Therefore, the solution is trivial. X equals to y equals to z is equals to 0. Let us consider one more example. X plus y minus z plus w equals 0. X minus y plus z plus w equals 0. X plus y plus z minus w equals to 0. Here 3 equations and 4 unknowns. That's why we can directly decide that rank is not more than 3. That's why rank is less than or equals to 3 and unknowns are 4. That's why rank of A is always less than unknowns in this case. That's why system must possess a non-zero solution. Zero solution is always solution. That is by default. 0 is always a solution. But is the system has non-zero solution? Yes, it has non-zero solution. We can directly conclude because rank is less than unknowns always for this system. Now this is the matrix A. By reducing it into row echelon form, this is the row echelon form of the matrix. It is in the row echelon form. Here number of zeros before first non-zero element in second row is 1. For second row, number of zeros before first non-zero element are 2. Zeros are increasing before the first non-zero element in every row. That's why this is in the row echelon form. Now solve this system using reduced equations. Here we come from the backward substitution. This is 2 into z minus 2 into w equals to 0. That is z minus w equals 0, z equals to w. Again from second row, minus y plus z equals to 0. That means y equal to z, and y equals to z, z equals to w. Y equals to z is equals to w. And again using this one, x plus y minus z plus w equals to 0. And y minus z equals already 0 here. That's why x plus w is only left, that is x is equals to w. See here, w minus z equals 0, w equals z, y minus z equals 0, y equals z, and first equation x plus y minus z w equals 0. Again already y minus z equals to 0, that's why x plus w equals 0, that is x equals to minus w. Therefore the solution is x is equals to minus w, w is a parameter. Any value of w, it is a solution, that is equals to minus 1, 1, 1, 1 into t, where w equals to t is a parameter. That's why the system has infinite number of solutions. Any constant multiple of the vector minus 1, 1, 1, 1 is a solution to the system. That is minus 1 by 2, 1 by 2, 1 by 2, 1 by 2 is also solution. Minus 2, minus plus 2, 2, 2 is also solution. Minus 3, 3, 3, 3 is also a solution. Like that we have, if the system possesses infinite number of solutions. Now this is the homogeneous system. Homogeneous system is always consistent and it possesses non-zero solution when rank of A is less than number of unknowns. Now this method is also used in so many softwares to solve the linear system of equations. Okay, this is the solution for the linear system of equations by using the rank method. Thank you one and all.